In this video, we're going to learn about the mole concept. By the end of the video, you should be able to explain the relationship between the mole and Avogadro's number. You should be able to use Avogadro's number to convert from moles to particles and particles to moles. And you should be able to use the periodic table to find the molar mass of some elements and some compounds. So the first thing you guys want to know here is that the mole, what it is, what is the mole? So let's take a look here. So 1 mole is equal to 6.022 times 10 to the 23rd power of atoms, molecules, ions, or any particles in chemistry. Then we also use something called a formula unit. A formula unit will be like, for example, calcium chloride is CaCl2, and it's not a molecule because the ionic compound is arranged in ions in this like crystal lattice shape where you have alternating charges, and so it's not a molecule. And so we have repeating units of, for every 1 calcium we have 2 chlorine ions. So this is what a mole is, and if you have this number, all the mole is a number. So just like 1 dozen is equal to 12, the mole is equal to 6.022 times 10 to the 23rd. Now, what does that look like in terms of size? So if we were to kind of write this out, so 6.022. Now it's to the 23rd power, so that means we have to move the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. And then our decimal is now in this position. And then in each one of these spots is zeros. So you can just, I know this is a little tedious, but just want you to get an understanding of like how big the mole is. Now, why do we have the mole? So in chemistry, I'm running out of room here. When we study chemistry, chemistry is a study of matter, and matter is really small. So the basic building blocks of matter are atoms, and those atoms are made by protons, neutrons, and electrons, and they're very, very tiny. So because in any, let's say, glass of water, we would have millions of water molecules, instead of counting them, the number of molecules would be ridiculous. It'd be super large. We can say that a large number of atoms, specifically 6.022 times 10 to the 23rd atoms or molecules, is equal to a mole. That way we can say we have 1 mole, 2 moles, 3 moles, 4 moles. So we don't have to say we have to this power, this ridiculous number of zeros. So if you kind of like look at the number, if your commas in here, your G3, it's insane. It's large. So the mole is super helpful for us to be able to count small things. And now another name for the mole is Avogadro's number. So this is Avogadro's number, and it's also called the mole. So they're one and the same. All right, so let's look at this first problem. This is how many molecules of water are in 2 moles of water. So first thing you want to do is write the number that you have to start. So we have 2 moles of water. So 2 moles, we'll just use H2O. And I always put this over 1. And in the directions it says complete the following conversions using dimensional analysis. So what's dimensional analysis? So dimensional analysis is the concept of canceling units out to move from one unit to the unit that you want. So you'll notice here that we are in molecules. They want to know molecules of water, but we have moles of water. So we need to be able to move from moles to molecules. And so just a perfect, good example here, I think, would be helpful. Let's say you wanted to know how many, 3 feet is how many inches? Okay, so 3 feet is how many inches? So the way you would set this up is you would put 3 feet little fraction, 3 feet over 1. And then in math, if you, let's say you take feet times feet, you get feet squared. But if you do feet divided by feet, then the units get canceled out. And so we want to get out of feet and we want to get to inches. And so if we put 1 foot on the bottom of the next fraction, now you have, what you have here is you have feet in the numerator and you have feet in the denominator. Much like I just showed you here, feet is in the numerator and feet's in the denominator. So the units cancel out, and 1 foot is equal to 12 inches. So now our feet canceled and we just moved into inches. And so 12 times 3 is 36 inches. And inches are the only surviving unit that didn't get canceled, so our answer is in inches. And then on the bottom, you could just, you could do 1 times 1 because they're next to each other. You do multiplication, but it's just going to be, 1 on the bottom, and 36 divided by 1 is 36. So this is the process of doing dimensional analysis. Now, I know you could have probably just said, hey, I know it's 36 inches because 12 inches are in a foot, and you can do that. But when you get into chemistry and you get grams and molecules and moles and atoms, and you get into all kind of different things, and it's hard to keep track of that in your head. So you use this skill of dimensional analysis to solve most problems here in chemical reactions. And anytime you're really dealing with quantities in chemistry, dimensional analysis is like the most, I would argue, is the most important skill for you to learn. So let's practice it. So we got moles of water on the numerator, and we want to get out of moles. So we want moles of water to be on the bottom. And then what is how are moles and molecules related? Well, we said 1 mole of water is equal to 6.022 times 10 to the 23rd molecules. And then our units, moles, cancel with moles. And now we're going to multiply 6.022 times 10 to the 23rd power in our calculator times 2 moles. And then we're going to get our final answer. Then our answer here is 1.20 times 10 to the 24th power. And the units are molecules of H2O. Now, the hardest part about this will be putting this in the calculator properly. You got to be able to type in 6.022, and you got to be able to, properly type in times 10, and then this 23 is raised up to the power of 23. So just practice with that. Make sure you're getting the same answer as I am. And this was right. This was a 2-0, not a 2-6. All right, so let's do the next one. How many moles are equal to 1.20 times 10 to the 24 atoms of oxygen? Now it's interesting. We have atoms of oxygen, and we have the same number as we got our answer in number 1. Let's go ahead and look at it. So 1.20 times 10 to the 24th power, and it's atoms of oxygen. I'll just put an O for oxygen because the symbol for oxygen is O. And then over 1. And then we want to cancel atoms of oxygen. So we're going to put atoms of oxygen on the denominator. And then there's 6.022 times 10 to the 23rd, which is the mole, our Avogadro's number. And that's equal to 1 mole of oxygen atoms. I don't know why I'm putting oxygen atoms. I'm just going to put 1 mole of oxygen. And so at this point, I'm going to multiply the 1.20 times 10 to the 24th times 1, which is going to get me 1.20 times 10 to the 24th on the top. And then I'm going to multiply 1 times 6.022 times 10 to the 23rd. And that's just going to get me the same number because multiplied by 1. Then I'm going to divide these two to get my answer. And my answer here is 1.99. So which is almost 2 moles from what I got in number 1. And it's moles of oxygen for that. Okay. And then let's go to number 3 here. So number 3, how many atoms are equal to 2 moles of sodium? So 2.0 moles of sodium, and sodium symbol is Na. We'll put that over 1. So we don't put anything down there. And then we need moles of sodium on the denominator. Why do we need that? We need to be able to cancel these units, moles on the top, moles on the bottom. And they want to know how many atoms are equal to that. So what do we know about atoms and moles? 1 mole of sodium is equal to Avogadro's number, or the mole, 6.022 times 10 to the 23rd atoms of sodium. We're going to multiply those together. 2 times 6.022 times 10 to the 23rd. Our answer here is 1.20 times 10 to the 24th atoms of sodium. Now what's interesting, I want you to take a look at this, is we had 2 moles of sodium and we had 1.20 times 10 to the 24th atoms of sodium. Now if you take a look at above what we had, in the previous one we had almost 2 moles of oxygen. And 2 moles of oxygen was 1.20 times 10 to the 24th atom. So whether you have atoms of oxygen or whether you have atoms of sodium, 2 moles is the same number of atoms. 1 mole is 6.022 times 10 to the 23rd atoms. And so we have the same quantity of atoms regardless of the kind of substance that it is. All right, let's do number 4. So, all right, for number 4, it says, how many moles are equal to 4.15 times 10 to the 23rd molecules of CO2? So what we'll do here is we'll start with our 4.15. Let me actually go back and just do black here. So 4.15 times 10 to the 23rd molecules of CO2. Set up our fraction. This is a 1, and so there's 6.022 times 10 to the 23rd molecules of CO2 in 1 mole of CO2. We're using Avogadro's number again. Our molecules will cancel out because the molecules are in the numerator and the denominator. And then we got to multiply 4.15 times 10 to the 23rd by 1. And we got to multiply 1 times 6.022. So all we're going to be doing here is 4.15 times 10 to the 23rd divided by 6.022 times 10 to the 23rd to get our answer. The answer here is 0.689. So 0.689. And the units are, all that was left was moles. So it's moles of CO2. Now what's important to note here is that we have just over half a mole. 1 mole is 6.022 times 10 to the 23rd. So we don't have quite a mole. Now just think about this. If we had a mole of molecules, we would have 6.022 times 10 to the 23rd molecules. We only have 4.15. So already, like when we see this number, we should expect that we're going to have less than a mole because 4.15 times 10 to the 23rd is less than 6.022 times 10 to the 23rd. All right, let's do this next one. How many molecules are equal to 2.5 moles of sulfur dioxide? So we have 2.5 moles of SO2, which is sulfur dioxide. Put that over 1. And then we need moles on the bottom. So we're going to do moles, sulfur dioxide on the bottom so we can cancel. And we got to go to molecules. So 1 mole, or I should have put moles, 1 mole of SO2 is equal to 6.022 times 10 to the 23rd molecules. Remember, Avogadro's number works for molecules, atoms, ions, particles. And so then we're just going to multiply 2.5 times 6.022 times 10 to the 23rd. And then we'll get our answer for that one. So this one comes out to be 1.5 times 10 to the 24th molecules. Now notice Avogadro's number is to the 23rd power. We're here to the 24th power. So we're way bigger than a mole. And we started with 2.5 moles. So this number makes sense to us. All right, number 6, how many moles are equal to 2.4 times 10 to the 23rd formula units of sodium chloride? So we start with the 2.4 times 10 to the 23rd formula units. formula units of sodium chloride, set up a fraction, and then there's 6.022, which is Avogadro's number, times 10 to the 23rd formula units. I'll just do formula units of sodium chloride in 1 mole of sodium chloride. So if you had a mole of sodium chloride, you would have that many formula units, but let's see what you have here. So we're going to multiply 2.4 times 10 to the 23rd times 1 times 6.022 times 10 to the 23rd. So it's 2.4 times 10 to the 23rd divided by 6.022 times 10 to the 23rd. And then our only unit is the mole, so our answer down here will be moles of sodium chloride. So let's see what we get here. So our answer here is 0.398. So we'll just say 0.40 moles of sodium chloride for number 6. And then in this last part, we're going to use the periodic table to find the molar mass of some of the compounds we just looked at. So I think one of the first compounds we had was H2O, or water. We had, I think, carbon dioxide. We had sulfur dioxide. We had sodium. And then we had, I think it was oxygen, which is O2. Okay, so how do you do this? So the molar mass. Let's just identify what the molar. So molar mass is, let's write it, molar mass is equal to the grams of a substance per mole, per 1 mole. Okay, and so you can find the grams. Now, why is grams important? Well, grams are important because grams is a unit for, so mass is measured in grams. So if you were to go in the chemistry lab and you were to put a substance onto a scale, you could measure the mass. And that's what we would be dealing with physically in a chemistry lab. And so now what we have is we have a mole, which is 6.022 times 10 to the 23rd. And that's the number of particles, atoms or molecules or ions. And then that relates us to mass, or grams. And then now we can look at how much we might have in a chemical reaction. So let's take a look at this. So how do you find the molar mass of a substance? How many grams you might have? So what you do is you look at the periodic table. So water is made of H2O. And so if you look at element number 8, oxygen, there's a number there at the bottom. So the 8 is the number of protons at the top. And then 15.999, that's the molar mass. That's the mass of a substance, or of the element oxygen. So if you had a mole of oxygen atoms, it would weigh 15.999 grams of oxygen. But then in water, we also have hydrogen. And hydrogen has a mole of hydrogen atoms would have a mass of 1.008 grams. And so what we could do is we can, underneath, or we'll just do it underneath here. So we'll do hydrogen. We said it's 1.008. But then if you look at the formula, it's H2. So that means we have to multiply the 1.008 times 2. And then for oxygen, we said it was 15.999 from the periodic table. And then there's only one oxygen, H2O1, right? We don't write ones in chemistry. And then what we can do is we can multiply the 1.008 times 2, and then add it to the 15.999. And what we'll get is 18.02 grams. And this is per mole. So if you had a mole of water, it would have a mass of 18.02 grams. All right, let's do another one. All right, so CO2. So carbon on the periodic table has a mass of 12.011. It's element number 6. And then we already saw oxygen was 15.999, so we're going to use both of those. All right, so let's write this down. So 12.01, and there's only one carbon, so we can just write 12.01. And then oxygen, let me just put carbon here and then oxygen here. 15.999, but there's 2 oxygens in the formula, so it's 15.999 times 2. And then we'll add these up. And what you'll get is about 44 grams per mole. So if you had a mole of CO2, it would have a mass on the scale of 44 grams. All right, then if we look at sulfur dioxide, SO2, we can see sulfur has a molar mass of 32.066. It's element number 16. And then dioxide is 2 oxygens. We can just use that 15.999 again. So here we go. So for sulfur, 32, I mean, just not messing that up. To 32.066. There's 1 sulfur. And then for oxygen, it's 15.999. And it's times 2. We can add these up. So it's 31.998. And then plus the 32.006 or 066. And we're going to have 64. So I'll just keep it at 64, about 64 grams per mole for SO2. All right, and if we take a look at sodium. So sodium has a molar mass of 22.990. So 22.990. And so if we had a mole of sodium, it would be 22.990 grams per mole. And we're done with that one because it's just sodium atoms. So we have nothing else, just pure sodium. And then our last one, we saw that oxygen was 15.999. But there's 2 oxygens in this molecule of oxygen. So it's 15.99 times 2. Just oxygen. So 15.999 times 2. So we're about 32 grams per mole of oxygen. So when you look at all of these, right? So you take a look at all these. Who has the highest mass per mole? So sulfur dioxide is 64 grams. So SO2 we do it up here, has a higher molar mass than CO2, which is higher than oxygen at 32, which is higher than sodium, which is greater than water. So why is that the case? Well, if you look at the individual atoms, sulfur has if you had a mole of sulfur atoms, it weighs 32.066 grams. That's the largest atom in all these molecules, and all these molecules have generally 2 or 3 atoms that make up the molecule. And so when you have a 32 grams per mole for sulfur, that's going to contribute to a lot of the mass. And if you look at the periodic table, you can see that sulfur on the periodic table has the most protons and the most neutrons. And if you remember, what is mass equal to? So mass is equal to the protons plus the neutrons, right? So if you kind of take a look at this on the periodic table, let me move that. So if you look at this, sulfur has a molar mass of 32, right? So when you look at like mass, right? Mass is equal to protons plus neutrons. And so sulfur has 16 protons and it's about a mass of 32. So it's got about 16 neutrons to be 32. Did I say that? Yeah, 32. So no one else here of the ones we wrote down. So oxygen was only 15.99, right? 16 grams. Hydrogen was 1 gram per mole. Sodium was 23. So it was interesting that sodium actually, if you had a mole of sodium was more massive than a mole of water. Even though water had 3 atoms in it, H2O, a mole of sodium would weigh more because each sodium atom has a mass of about 23 grams. A mole of sodium atoms had a mass of 23 grams, but a mole of water only has a mass of 18 grams because hydrogen is much smaller as an atom. So you can have the same number of particles, a mole of many substances, but because each substance has a different atoms in it, and those atoms have different atomic structures of protons and neutrons, a mole of sodium and a mole of water won't weigh the same, right? Generally speaking, if you have 2 or 3 of the same object, like if you have a dozen pencils, right, they're likely to be similar in mass. Or if you have a dozen eggs, they might be similar in mass. But in chemistry, when you have a mole of something, when you have the same quantity of something, and that something is different, iron or gold or platinum, because gold and iron have different numbers of protons. Here's iron, and here's gold. A mole of gold and a mole of iron, who's going to be more massive if you have the same number of gold and iron atoms? Well, gold will be, because each gold atom has 79 protons, but each iron atom only has 26 protons. And mass is determined by protons and neutrons. And so since gold has way more protons and neutrons, if you have the same number of those atoms, a mole of each, the gold will be heavier in your hand. Hopefully this helped. If you have any questions, if there's any other topics in chemistry that you're struggling with, that you're having a tough time with, please leave a comment. Let me know what that topic is, and I'd be happy to do a video on that particular topic.